Hi, welcome back to FanBam. So today's topic is energy, and specifically we'll be talking about the difference between kinetic energy versus gravitational potential energy versus spring potential energy. So over here we have the examples of the equations you use for every specific type of energy, type of energy. So for kinetic energy, we have 1/2 mass times velocity squared. For gravitational potential energy, we have mass times gravity times height. And for spring potential energy, we have 1/2. This is the constant of the spring constant, and then the distance squared. You can see that US, which is the spring potential, is very similar to kinetic energy. You just change the variables. It's similar because you're using a spring. The potential of the spring is basically the kinetic energy that it's using. That's why it's very similar. Kinetic energy is the energy of motion. Any object that has motion in any direction has kinetic energy. The equation we already saw. Potential energy is an object that can store energy, and as a result of its position. So the higher the object is, the more potential energy it will have. Gravitation. There are two types: potential energy for using gravity, and then potential energy using spring. Sometimes is known as elastic because springs are elastic. The potential energy using gravitational is energy stored in an object as a result of gravity pulling on the object towards the center of the earth. And spring potential energy, otherwise known as elastic, is energy stored in an elastic material as a result of their stretching or compressing. We can move on to this problem over here. We have some type of base holding up a string, and on this object we can see that it's pulling down on the spring, and causing it to stretch. So for this problem, the question would be, what is the total energy of the mass spring system? This shown below. Well, in this case above. The mass is shown at the maximum displacement on the spring, 5 meters from the equilibrium point. So the equilibrium point would be where the spring is at its normal resting position. So we can see this is not to scale, but the spring would be this big, and since this weight is pulling down on the string, it grows a little, and it comes 5 meters from the equilibrium point. So here we have a system of two conservative forces, mass and gravity. Even if there were more than one conservative force acting on the system, it's still a conservative force. So let's say that only gravity was affecting this, which you would still need a mass, but if only gravity was working on it, it's still conservative force. Thus potential energy is defined, and we can calculate the total energy of the system. Since the quantity is constant, we may choose any position for the mass that we like. In this case, we've chosen a point where mass has no velocity. So UG, which equals mgh, equals the -5 because it's going down. Mass times gravity, and if we plug that in, we have -5. The mass is 5 kilograms, and then gravity is 120. We end up having negative 245 joules because we're talking about energy. For the spring, we have 1/2 the constant times distance squared, which is 1/2 10. That's the constant. And the distance is 5 squared. And we end up having 125 joules. And total energy, we would multiply, add these together. So UG plus US will equal these two numbers, the negative 245 plus 125 and a negative 120 joules. That's your problem. For this topic and a lab that you can do the conservation of energy lab. And in this experiment, you will use a ramp and a marble to investigate the conservation of mechanical energy. This is only one of the examples we can use. Simple objects that you have at home. You can have a table, a marble, meter stick, a timer, and you can find the components for it. For the analysis, you can calculate the average horizontal distance in meters traveled by the marble. Calculate the time elapsed, so how much time it took for the ball to leave the ramp until it hit the floor, where gravity is equal to acceleration due to gravity. Calculate the horizontal velocity of a marble when it's at the bottom of the ramp, and calculate the potential energy of the marble at the top, which would be potential energy. And then you can calculate kinetic energy once the marble has left the ramp and hit the floor. A typical conclusion that you can get out of this is if the mechanical energy was conserved as the marble went down the ramp, you should have the amount of potential energy at the top of the ramp compared to the amount of kinetic energy at the bottom of the ramp. So you would have to calculate, and every experiment turns out differently, of course, but that's a usual thought that you would have, that the potential energy that you have is the kinetic energy that you're using. Another question for your conclusion would be, find a difference between your calculated values for potential and kinetic energy. How close were these values? What was the mechanical energy conserved? So you would find what is called, all right, you can find total mechanical energy because you already have potential and you would have kinetic energy, and that way you find how much energy did you truly use. Explain how your lab results can be consistent with the law of conservation of energy. Where did the missing energy go? So there's times where you use more kinetic energy than you have potential, meaning that that there was something extra causing more energy than you originally thought you had. So you would have to calculate what and where that energy went. It could be due to air resistance, or there could have been some type of obstacle that the marble took longer for it to reach the ground. And that was harder to find. It took more energy to find them, to hit the ground. Sorry. And that's it.